Hi, folks. In Dalton's atomic theory, he stated that all atoms of a particular element were identical. But with the discovery of atomic radioactivity and the three fundamental particles of electrons, protons, and neutrons, a more sophisticated picture was emerging about the nature of the atoms within an element. We know that each element is unique because of the number of protons. Atoms of the same element will have the same number of protons. Now, what becomes a bit disconcerting is that the mass of the atoms of the same element found in nature can vary substantially.
It was soon discovered that though elements are made up of atoms, all having the same atomic number, thus the same number of protons, not all the atoms of the same element were identical as far as mass and number of neutrons. Atoms that have the same number of protons but a different number of neutrons are called isotopes. For example, there are three major naturally occurring isotopes of carbon. In their neutral uncharged form, we write them down as shown. Let's look at the symbolism we will use to describe different isotopes. We will use the charged anion of carbon-12 as an example. We know the subscript on the left is the atomic number and equal to the number of protons, and the superscript on the right is the charge of the atom and will give us the number of electrons relative to the number of protons. In this case, we have 4 more electrons than protons. Now, the superscript value on the left is the mass number and is the sum of the number of protons and neutrons in the nucleus of this isotope. And you can see that for atoms of the same element and atomic number, the mass number distinguishes or identifies the particular isotope of the atoms. So looking at the example, we know we have 6 protons from the atomic number identifying the element as carbon, and we have 10 electrons because there are 4 more electrons than protons to give us the anionic charge of -4. And finally, there are 6 neutrons in the nucleus of this isotope because the mass number is 12, and because subtracting 6 protons from the mass number value gives us 6 neutrons. Now, you'll also see isotopes written as carbon-12, carbon-13, and carbon-14, where the atomic number is assumed and redundant since you're using the name of the element in this type of isotope description. Now, about 98.93% of natural occurring carbon is carbon-12 isotope, 1.07% is carbon-13, and there is only a small trace amount of carbon-14 in nature. And there are also many new synthetic carbon isotopes that have been made in the last 80 years. Now let's look at the most prevalent natural occurring oxygen isotopes. About 99.757% of natural occurring oxygen is oxygen-16, and then 0.038% is the oxygen-17, and 0.205% is the oxygen-18 isotope. So why was the old oxygen standard such a great standard for so many years for producing relative atomic masses? We now see that it was because natural occurring oxygen was almost a single pure isotope, oxygen-16. Remember our measurement of relative atomic masses, the numbers written below the elemental symbol on our periodic tables? Well, we mentioned this earlier, but the modern standard atom that we compare each element's atomic mass against is now the carbon-12 isotope, which is given a standard value of exactly 12. And this supplanted the venerable old oxygen-16 standard. Using this new standard, we established a new mass unit, one that is very small and useful for talking about the mass of individual atoms and subatomic particles, like protons, neutrons, and electrons. This mass unit is defined by taking the actual mass of a single carbon-12 atom, 1.992646 times 10 to the minus 26 kilograms, and dividing it by 12. and we call the resultant mass an atomic mass unit, or an AMU for short. Another way to think about it is that we have established, by convention, that one carbon-12 atom should weigh exactly 12 AMU. This standard leads to another important constant that we know and love. If we had a particle that weighs exactly 1 AMU, and if we gather an Avogadro's number of these particles, or 1 mole of them, we can establish a set number of particles so that this 1 mole of 1 AMU particles weighs exactly 1 gram. This set number of particles is obviously Avogadro's number of particles. And the value for Avogadro's number is our old friend 6.0221409 times 10 to the 23rd particles. So you see, our modern value for Avogadro's number was established and standardized after we discovered isotopes and established the carbon-12 standard. We also can establish an SI unit for electrical charge. We now know that any matter that is charged must have a magnitude of charge that is equivalent to an integer value of electrons multiplied by the charge of a single electron. The SI unit for charge is a coulomb, or capital C, and the value of 1 coulomb of charge has its history linked to the development of batteries by Volta and others. When a battery puts out a charge of 1 coulomb, it has in effect produced 1 joule of energy. The charge of a single electron in this new SI unit is equivalent to minus 1.602177 times 10 to the minus 19th coulombs. Now we also know that charge actually should also have a sign associated with it to tell us if it is a negative or positive charge. Now, if we have 1 mole of electrons, we find that multiplying the charge of a single electron by Avogadro's number of electrons gives us a total of 96,485.33 coulombs of charge, which we call Faraday's constant. Now, I admit, these are some funky and unwieldy numbers to use when talking about the charge of atoms and atomic particles. To make it simple, when talking about the charge of a single atomic particle or atom, we will establish charge in units relative to the charge of a single electron. Doing this, we can set the relative charge of an electron to be minus 1 electron units, and that of a proton charge to be equal but opposite, plus 1 electron units. Now, we typically will not say electron units, but simply minus 1 charge for an electron and plus 1 charge for a proton. Thus, if we say a cation has a charge of plus 3, we not only know that there are 3 fewer electrons than protons in the atom, but also that a single atom of this cation has the same magnitude of charge in coulombs as 3 electrons. Okay. So let's summarize our findings of atomic particles into a simple, comprehensive table describing all the properties of the small particles that make up atoms. We saw above that the mass of a carbon-12 atom is 1.992646 times 10 to the minus 26 kilograms. And using a modern instrument called a mass spectrometer, we find that the mass of a carbon-13 atom is 2.159257 times 10 to the minus 26 kilograms. So first, let's calculate the relative atomic mass of a carbon-13 isotope versus the carbon-12 standard in unitless terms. We divide the mass of a carbon-13 atom by the mass of our standard carbon-12 atom and multiply by the standard value 12 to produce our relative atomic mass for this isotope. The number obtained is 13.003355. We can also compute the mass of the carbon-13 atom in atomic mass units, or AMU. We take the weight of the carbon-13 atom and divide by the AMU to kilogram relationship. And we find that the magnitude of the number we compute is 13.003351, and is almost the same as what we just obtained before, but now it has a unit of mass attached, AMU. Now, let's calculate the mass of 1 mole of carbon-13 atoms. If we take the mass of a single carbon-13 atom in kilogram and multiply it by Avogadro's number of carbon-13 atoms, which is 1 mole of carbon-13 atoms, and use the kilogram to gram conversion to get the final value in grams, we again get about the same value as the last two computations, but with a different set of units. 13.003350 grams per mole of carbon-13 atoms. Now, all these results gave us the same magnitude plus or minus a bit at the end due to round-off errors in our constants. The similarity of these results is not a surprise because all three computations required values and conversion relationships based on the same carbon-12 standard. The point of the exercise is that the relative atomic mass number can be interpreted in one of three ways. It can be interpreted for what it is, a unitless relative atomic mass of the carbon-13 compared to the carbon-12 standard. It can also be the magnitude of the mass of one carbon-13 atom in AMU. And finally, and the most useful interpretation when doing lab work, the number can be used as the mass in grams of 1 mole of carbon-13 atoms. All three interpretations have the same magnitude. We just attached different units to the number based on our needs. So we should be able to interpret the relative mass values found underneath each element on the periodic table in the same way. But we can't yet. There's a small difference in the actual interpretation of the number on the periodic table that we must consider first. Take a close look at the relative atomic mass ratio for carbon on your periodic table. And we find a value of 12.01, not 12. That's because, as we noted earlier, only 98.93% of natural occurring carbon on Earth is carbon-12. 1.07% of carbon is the heavier atom, carbon-13. Again, this kind of data is relatively easy to obtain using a mass spectrometer these days. Now let's work this out. If we were to dig up a mole of carbon atoms, what would be the average mass of a carbon atom? We know that 98.93% of the carbon atoms will have the same mass as a carbon-12 atom, and 1.07% of them will have a mass equal to a carbon-13 atom. So let's calculate the average mass of a carbon atom using the relative atomic masses of each of these atoms. Like a good student, I first check to see if my given percentages add up to 100%, and we see it's close enough. Now let's do the computation. 0.9893 times 12 plus 0.0107 times 13.00335 equals 12.010735, which rounds off to 12.01. Yes, this is the value on the periodic table below the symbol, keeping in mind our sig fig math. So the relative atomic masses we find on the periodic table are actually the weighted averages of the natural occurring isotopes for that atom. Bottom line, the number typically found below the element symbol on the periodic table represents the weighted average mass of a natural occurring carbon atom and can be interpreted to be the mass, in grams, of 1 mole of the element when you dig it up from nature. Wonderful. Now, let's see what types of calculations we can do with this new quantifying atomic data. Now, if we have 45.0 grams of naturally occurring sulfur, how many moles of sulfur do we have? Okay, so the solution map is grams of sulfur to moles of sulfur. Now, we need the link between grams of sulfur and the moles of sulfur. Looking at the relative atomic mass of sulfur in the periodic table, we see that the number is 32.069, and we know that we can interpret the value as 32.069 grams of sulfur equals 1 mole of sulfur. There is the link we need. So setting up the ratios so units cancel correctly and doing the computations, we obtain 1.40 moles of sulfur, a value that should have the same number of sig figs as the original given value of 45.0 grams. Now, knowing the moles, how many atoms of sulfur do we have? Well, the link between the moles and number of particles is Avogadro's number, our moles particle equivalent. Here we simply multiply the number of moles by Avogadro's number to obtain the number of sulfur atoms. Now, if I have 0.244 moles of sulfur, how many grams of sulfur do I have? This should be simple enough. It's like our first problem, but runs in reverse with the moles-grams relationship for sulfur inverted to cancel the units correctly in the computation.
Terrific. We now can quantify matter either by mass or by number of particles if we know what elements that the matter contains. Quite a huge deal. Now we just need to answer the more complex question of what factors dictate the reactivity of the elements and makes the periodic table look, well, periodic. The secret lies with electrons. Oops. That was another spoiler alert. Anyway, catch you later.